Welcome back, chemistry fans. We get to start a brand new unit today. This is unit 4, topic 1. We're going to talk about molar mass. It's a very, very simple concept. We just get to add some weights together from the periodic table. Okay, so here, let's jump into it and make the most of our time together. So molar mass needs to be distinguished from an atomic mass. An atomic mass from our periodic table is just the weight of the individual element, all the average of all the isotopes. Remember, isotopes are elements that have different numbers of neutrons, so they weigh something different. We average those together to get this average weight for any individual element. That can be found on each box for the periodic table. Well, what we're going to do today is we're going to take a step forward and we're going to say, well, what happens if we start adding them together to make molecules? So if we have a compound or a molecule, what we've got to do is we got to take those weights, add them together to find out what is the overall, the total, the sum of the weights. And we call this the molar mass. So if hydrogen weighs 1 and there are 2 of them, that's 1 plus 1. And oxygen weighs roughly 16. We add all 3 of those together and we would get that 18 as the molar mass. All right. Now, if I'm going to do the same thing for different elements, the process never changes. All I would do is I would go and look up the weight, and depending on how many atoms there are, I would then apply that value to it. So in this first one here, there is 1H, there's 1Cl. I go and look up their weights. I add it together, I get 36. Now, on the next one, I've got 6 carbons. So that means 6 times the weight of carbon. Well, if I look on the periodic table, carbon would weigh 12.01. So I'd multiply that by 6 to get the 72. My oxygens, there are 12 of those. So that'd be 12 times 1.0079. And that weight is the 12.084. And then for the oxygens, there are 15.994. There are 6 of those. I would multiply that, and that's where the 95.9 comes from. I add all 3 of those new values together to get my total value of 180. All right, well, let's do the same thing. So we are going to now, whoops, things have changed on this one. So I need to change my first examples here, I think, a little bit. Yeah. So what we're going to do is make all of these, I'm going to change these a little bit. So we're going to make this one sodium. We're going to make all of these 1s. We don't need to change the moles. It's hard enough as it is. Okay. So let's go and look up the weight of neon. Now, neon weighs off the periodic table. Let's find out here. Neon is over here at element number 10. It weighs 20.180. So that's its atomic mass, but it also happens to be the weight that we, it also happens to be the weight that we are looking for. So 20.10. Did I say that? I don't remember what I just said. 20.180. So I dyslexically switch those 2 numbers, 180. Okay. The units on this are grams per mole. Sodium. Let's go and look up how much does sodium weigh. Very simple again, simple task. Sodium's over here, 22.990. 22.990. 22.990. How about oxygen? Well, here's a trick. What do we know about oxygen? Oxygen is a diatomic molecule. There are Brinkelhoff elements. There are 7 of them off of the periodic table that we must be aware of whenever we do this. Now, so what that means is I've got 2 of these oxygens that weigh 15.994. So I'm going to add those together and, or I'm going to, add them together, or you could just do 2 times 15.994 off the periodic table and you get 31.998. Well, that's too many. Oh, no, that's correct because I missed one of the 9s, 9994. All right. Water, H2O. Each one of the waters weighs, or each one of the hydrogens weighs 1.00794, but there are 2 of them. And then there are 2, and then there's only 1 of the oxygens. Each oxygen weighs 15.9994. So I'm going to add all that together. So 1.00794 times 2 plus 15.9994. And that gives me 18.1528. Now with sig figs, there are only 4 values here that I can use. So this actually would round up to 0.0153. Carbon dioxide, carbon weighs 12.01. Let me see, 12.01009, actually, 009. And there are 2 of the oxygens, 15.9994. So let's add that together. 15.9994 times 2 plus 12.009. And we get 44.0078 grams per mole. Again, grams per mole on all of these units. Grams per mole, grams per mole. Make sure you're putting your units in. All right, carbon, 12.009. plus 4 of the hydrogens, 1.00794. All of these values are exactly calculated the same. This is just practice. None of this should be hopefully difficult for you. 0.00794 parentheses, and you would get a sum of 16.04076 with sig figs. I'm only allowed to use 3 sig figs. That cuts off. My final answer would be 16.041 grams per mole. Okay, so this is the process of what we need to understand today. Now let's understand how we know this to be true. There are 2 laws that we need to be aware of called the law of definite proportions. The law of definite proportions says that if you have carbon dioxide, it will always be made of 1 carbon and 2 oxygens. That seems very, very obvious to us. But again, when these laws were written, that wasn't the case. And so what they did is they took carbon dioxide and they split it up into its percent compositions, and they were able to prove that those percentages match up with their atomic masses. Water will always be water. Now, the law of multiple proportions says that, okay, so even though we know that carbon dioxide is CO2, there is also the chance that I could make CO, carbon monoxide. And so even though you have the same elements, you can mix them up into different proportions. And you have to be aware of that when we are calculating our masses. So it does always depend on what the ratio is as to how we calculate them. All right. One other detail that we have that proves that molar masses are true is Millikan's oil experiment, whereby he sprayed oil into a tiny hole and then put an electrical charge on it. And he was able to count the number of oil droplets that are in a certain space, and that would tell him what the charge every single electron is carrying, because he would assume that there could be 1 electron on each one of these drops. So with a very ingenious experiment, he was able to calculate what is the charge and what is the weight mass of electrons. All right, this is everything that I wish to share with you today. So thank you very much for your time. I will talk with you again next class. Bye-bye.